Hello, in this lecture we will talk about the limit of a sequence. A sequence is a set of numbers. For example, the sequence 157 is a sequence that contains three elements. Here, the sequence 157 contains three elements. It is a group that contains three elements. And actually, the sequence can be finite or infinite. This sequence is a finite sequence that contains only three elements, while the sequence of the natural numbers, that is to say, the sequence of the natural numbers are 1, 2, 3, 4, 5, until n. This sequence contains infinite numbers. And when we talk about the limit of a sequence, we only refer to infinite sequences. Okay? Like the natural numbers. And the limit of a sequence is a number to which the members of the sequence get closer and closer, so that the distance between the members and the limit is as small as we like. For example, the sequence an equals to 1 over n contains, so the first member is the member that when n equals to 1, we get that the first member is 1 over 1. The second member is the member that we will get that when n equals to 2, that is to say it is 1 over 2. The third member is the member that we get when n equals to 3, that is to say it is 1 over 3, etc. until 1 over n. And as you can see here, the members of this sequence are getting closer and closer to 0. And therefore the limit of this sequence will be equal to 0. That is to say, L, the limit of this sequence, is 0. Or we can write down that lim, the limit of this sequence an, when n tends to infinity, is equals to 0. Why? Because the members of this sequence are getting closer and closer to 0 whenever n increases, then the members of this sequence are getting closer and closer to 0. Okay, therefore the limit of this sequence an equals to 1 over n is equals to 0. So when a sequence actually that has a limit is called convergent sequence, while if we talk about a sequence that has no limit, is defined as divergent sequence. And actually, the claim that the sequence an when n goes from 1 to infinity, if the limit of this sequence equals to n, so that is the way that we will write down that the limit of this sequence an, when n goes from 1 to infinity, is equals to l. Another way to write down that the limit of this sequence is equals to l is to write down that lim, it is the limit of this sequence an, when n tends to infinity, is equal to l. Okay, so those are the two ways to write down that the limit of a sequence is equals to n. Either we can write down that an, the sequence an, when n goes from 1 to infinity, is equals to l. L is any real number. And the second way to write down that the limit of sequence an is equals to l is to write down that the lim of an is the name of the sequence, when n tends to infinity, is equals to n, is equals to l. Again, l is a real number. I will repeat again that A indicates the sequence, the letter A indicating the sequence that the members are belong to, and the N is the serial, is the index of the sequence. That is to say, when n equals to 1, here we get A1. That is the first member of the sequence. When n equals to 2, we get the second member of the sequence, that is A2. When n equals to 3, then we get A3, that is the third member of the sequence, etc., etc. Okay? And the sign, this sign, symbolizes the concept of infinity. Okay? So, for example, if we have the sequence an equals to 1 over n, then the first member, we can get the first member of this sequence when n equals to 1, so it is 1 over 1. The second member of the sequence is when n equals to 2, that is to say it is 1 over 2. The first member of the sequence is when n equals to 3, that is to say it is 1 over 3. Okay. So, what is the definition of a limit of a sequence? Intuitively, a real number A is a limit of a sequence if the members of the sequence are getting closer to it. Okay, so for example, if A is the limit of a sequence, then the members of a sequence are getting closer to A. Okay. However, this definition is vague and not useful. To give more precise definition, the conceptions, the concepts of environment and distance must be used, which will apply to the members of the sequence from a center place onwards. So, when we say that the members of the sequence are getting closer to the limit, so the meaning of close to the limit, what is the meaning of close to the limit? The set of numbers of distance from a given value A doesn't extend any fixed size is called an environment of A. In this context, it is customary to use the Greek letter epsilon to represent the radius of the environment. The radius of the environment is a positive number. That is to say, epsilon is greater than 0. And epsilon can be as small as we like. So the environment includes all the numbers that satisfy the condition x minus a is less than epsilon, or the absolute value of, so if an is the member of the sequence and L is the limit of the sequence, then an minus L, the absolute value of n minus L, must be less than epsilon, and epsilon itself is usually a small number that is greater than 0. Okay? So the absolute value of an minus L must be less than epsilon. So actually, I'll repeat again that if A is the limit of the sequence, and the radius of the sequence is epsilon, then the environment of A it actually will be A minus epsilon and A plus epsilon. So if the limit of a sequence, of any sequence, is equals to A, then most of the members of the sequence must be located inside these brackets. Why? Because all the numbers that are located inside those two brackets are defined as the environment of A. So if a sequence has a limit, then most of the members of the sequence must be located inside these brackets. That is to say, most of the members of the sequence must be located in the brackets that are starting from A minus epsilon until A plus epsilon. Okay? So you can see that the distance of each member of the sequence that are inside the brackets are less than epsilon. Okay? Each, for example, if the member of the sequence is located here, then the distance of this point from A is less than epsilon. Why? Because A plus epsilon equals to this number. Therefore, this point is the distance of this point from A is less than epsilon. Why? Because A plus epsilon minus A is epsilon, so that is to say the radius of this limit A is epsilon. Here the distance A minus epsilon, and A is also the radius is here epsilon. So each member that is inside each member of the sequence that is inside these brackets are actually is far away less than epsilon units from A itself. Why? Because here A plus epsilon is this point, so any member that is inside these brackets here will be located less than epsilon units from A. And here again, if this is the member of the sequence, then the distance between this member and A is less than epsilon. Why? Because epsilon itself is the radius of the environment. So any member that is inside the brackets is located less than epsilon units from A itself. That is the limit of the sequence. I repeat again that if the limit of a sequence is A, then most of the members of the sequence must be located inside the environment of A, and the environment of A are all the numbers that are inside those two brackets. Okay? again, not all the members of the sequence must be located inside the brackets, but from a certain index of n, that is to say, we choose the natural number NO, and all the natural numbers that are greater than NO, we get that the value of the sequence of the member of the sequence is AN. So AN minus the limit of the sequence, that is L, the absolute value of AN minus L must be less than epsilon. Okay? So if a sequence has a limit, then we must be able to find out a natural number NO, that from NO onwards all the members of the sequence will be inside these brackets, inside the vicinity of A. Okay? Okay? So any environment that we will choose for the limit that is A, most of the members of the sequence must be located inside the environment that we will choose. Again, the environment of A are all the numbers that are located inside the brackets. Okay? So if a sequence has a limit, then most of the members of the sequence must be located inside the environment, that is to say, they must be located inside the brackets. Okay? And because of the fact that until NO we have a finite indexes 1, 2, 3 until n, we have finite indexes. That is to say, we have finite members of the sequence that are not located inside the brackets, but from n until infinity we have infinite members. That is to say, we can say that if a sequence has a limit, then infinite number of members of the sequence must be located inside the vicinity of A, that is the limit of the sequence. Okay? Again, all elements of the sequence beyond NO are inside the brackets. Therefore, we can say that infinite number of elements of the members of the sequence are located inside the brackets, inside the vicinity of A, that is the limit of the sequence. Again, since n tends to infinity, until NO there is a finite number of indexes, and from NO until infinity we have infinite members that are located inside these brackets. Therefore, it will be the proof that A is indeed the limit of the sequence, because of the fact that infinite members of the sequence are located in the vicinity of A, that is to say, are located inside those two brackets. We can say that the limit of the sequence is A. So again, because of the fact that infinite number of indexes exist from NO until infinity, therefore it can be said that for all epsilon, almost all members of the sequence are at a small distance, that is epsilon, from the limit, that is A. And no matter how much we reduce the radius of the environment, always most of the members of the sequence will be located inside the environment of A, that is to say, inside the two brackets. Again, almost all the entire sequence are located inside those two brackets. That is to say, infinite elements of the sequence are located inside those brackets, and therefore A is the limit of the sequence. So actually, if we have a sequence AN that goes from 1 to infinity, we will say that this sequence converge to the real number L, that is to say, the limit of this sequence will be equal to L, or L is the limit of the sequence, and we will write down that, we can write down also that lim AN, when n tends to infinity, equals to L, we can also write down that AN tends to L. There is three ways to write down that the limit of the sequence of this sequence AN is equals to L. If for any positive real number epsilon, as small as we like, exists natural number NO, exists natural number NO, or exists natural number NO, so that for all n that is greater than NO, we'll get that AN minus L, the absolute value of AN minus L, is smaller than epsilon. Okay, so I'll repeat again. The limit of the sequence AN when n goes from 1 to infinite will be equal to L if for any positive real number epsilon that is greater than 0. So epsilon could be as small as we want. We have to find out a natural number NO. So for all n that is greater than NO, we'll get that AN minus L is less than epsilon. Okay, so if n is greater than NO, then we'll get that AN minus L, L is the limit of the sequence, and AN is the member of a sequence, then the absolute value of AN minus L is less than epsilon. We can write down also that for any epsilon that is positive, exists NO that is a natural number that is of course greater than 0, such for every n that is greater than NO, we get that AN, the absolute value of AN minus L, is less than epsilon. Okay, I'll repeat again. For every epsilon that is greater than 0, exists the natural number NO in such a way that for every n that is greater than NO, we'll get that AN minus L is less than epsilon. AN is any number that is greater than NO. So AN minus the limit L, the absolute value of AN minus L, is less than epsilon. Okay? Or we can write down that in another way, that L equals to lim AN when n tends to infinity. Okay? Actually, NO depends on epsilon. The smaller epsilon that we will choose, usually we will get that NO will be greater. Okay. So here L is any real number, but we can talk about limit in the broadest sense. That is to say, the limit of a sequence in the broadest sense could be also infinite. So it doesn't have to be L that is any real number, but it also could be infinite or minus infinite. And then we are talking actually on the limit in the broadest sense. Okay, so limit in the broadest sense. So we say that a sequence AN tends to infinity. That is to say, the limit of sequence AN is equals to plus infinity when n tends to infinity. If for any real number m exists a natural number NO, NO belongs to the natural numbers, so that for all n that is greater than NO, you will get that AN is greater than M. Okay? Again, the limit of the sequence AN will be equal to plus infinity when n tends to infinity if for any real number m could be as large as we wish. We can find a natural number NO, and for any n that is greater than NO, we'll get that AN is greater than M. Okay? And the definition of tendency to minus infinity is similar. Okay? I repeat again, the limit in the broadest sense, the limit of a sequence AN will be equal to plus infinity when n tends to infinity if for any big number m for any big real number m, we can find NO that for any n that is greater than NO, then AN will be greater than M. That is to say, in this way we actually proved that this sequence has no limit. Why? Because it is greater for any real number m that could be as great as we would like. M could be equal to gram number also. And we can find NO that belongs to the natural numbers. And for any small n that is greater than NO, then the AN, the value of the member, that is to say AN, will be greater than M. Again, in this way we proved that this sequence AN has no limit. Why? Because it could be greater than any big number M. That is to say, for that reason, the limit of this sequence is equal to plus infinity. And in the same way, we actually can define tendency to minus infinity in the broadest sense. Okay? Then we will define m that is a very small number. Then we have to find out NO that belongs to the natural numbers in such a way that for any n that is greater than NO, we'll get that AN is smaller than M. And then in this way we actually proved that the limit of the sequence is smaller than any small number that we will choose, and therefore the limit of the sequence is equal to minus infinity. That will be the definition of a sequence that its limit is minus infinity. Okay? So, as I already mentioned before, I'll give you another example. The limit of the natural numbers is plus infinity. So, the natural numbers, we will represent the natural numbers as AN equals to N. That is the definition of the natural numbers when N goes from 1 to plus infinite. So lim AN is equals to N, again when N goes from 1 to infinity, to plus infinity. The limit of this of the sequence of the natural numbers is equals to plus infinity. And why it is equals to plus infinity? Because we actually, if we choose any big number m, then we can find out NO that belongs to the natural numbers, and for any n that is greater than no, we will find out that an is greater than m. That is to say, in this way we proved that the natural numbers tend to infinity. Why? Because when n tends to infinity, then the value of the members of the values of the members of the natural numbers is greater than any big number that we would like to choose. M would be any big number, and still the members of the sequence will be greater than m. And because of the fact that the members of the sequence are greater than any real number that we will choose, then it means that they tend to infinity. That is to say, the limit of the natural numbers, of the sequence of the natural numbers, it is equals to plus infinity. Okay? And we also have the arithmetic of limits. So actually, if we have two sequences an and bn that converge in constant alpha, then we have arithmetic of limits. Again, if we have two sequences an and bn that converge in constant alpha, then lim an plus bn, when n tends to infinity, is equals to lim an when n tends to infinity plus lim bn when n tends to infinity. And we have also the second rule. Lim an times bn equals to lim an times lim bn when n tends to infinity. I'll repeat again. Lim an times bn equals to lim an times lim bn when n tends to infinity. And the third rule is that lim alpha times bn equals to alpha times lim bn and n tends to infinity. So actually it means that we can take out the constant alpha out of the limit. So we will multiply the constant alpha by lim Bn when n tends to infinity. So lim alpha times Bn equals to alpha times lim Bn when n tends to infinity. And finally, we have rule number 4, that lim An over Bn when n tends to infinity equals to lim An when n tends to infinity over lim Bn when n tends to infinity. And in this case, Bn cannot be equal to 0. Why? Because it is not allowable to divide by 0. Therefore, Bn cannot be equal to 0. And also, lim Bn when n tends to infinity cannot be equal to 0. Why? Because if lim Bn when n tends to infinity will be equal to 0, then it means that we are dividing by 0, and it is not allowable to divide by 0. Therefore, lim Bn when n tends to infinity cannot be equal to 0. Okay, so, and we have another rule. Another rule that a limit of a subseries a limit of a subsequence is called partial limit of the original sequence. And when a sequence converges, all of its partial limits are equal. Again, I repeat again. When a sequence converges, all its partial limits are equal. And the collection of all partial limits describes in a known sense the original series. So if we have a sequence that's divergent, then it will have more than one limit, and the collection of all partial limits of a sequence that is divergent, it is actually the original sequence. And the smallest partial limit is called lower limit, and the largest is called an upper limit. Okay, so we finished to talk about the limit of a sequence. Now I'll summarize the lecture. Okay. So when we talk about the limit of a sequence, we relate only to infinite sequences, because of the fact that if we are talking about a finite sequence, we actually don't have anything to talk about, because we know everything. We know here in this finite sequence that is 1, 5, 7, the first member is 1, the second member is 5, and the third member is 7. So it is not interested us at all, because we know everything about the sequence, and therefore when we are talking about the limit of a sequence, we relate only to infinite sequences. Okay? That is to say, we are talking about sequences that contains infinite members or infinite elements. Okay? So, what is the limit of a sequence? The limit of a sequence is a number to which the members of the sequence get closer and closer, so that the distance between the members and the limit is as small as we like. Okay? For example, if we are talking about the sequence an that is equal to 1 over n, the limit of this sequence is 0. Why? Because you can see here that as n it increases, the members of the sequence are getting closer and closer to 0. Why? Because when n equals to 10, the number of the sequence is 1 over 10, is 1/10. And if n equals to 100, then the number of the sequence, and n equals to 100, is 1 over 100, that is 0.001. So you can see that as n increases, we are getting closer and closer to 0. Therefore, the limit of this sequence, an equals to 1 over n, is 0. Why? Because whenever n increases, we are getting closer and closer to 0. So, a sequence that has a limit is, you can say that it converges, and if a limit is a sequence has no limit, then we can say that it's divergent. Okay? So here A is the letter A indicating the sequence that the members are belong to, and N is the index of the member. So the first member of this sequence AN is A1, the second member is A2, and so on. Okay? So if the sequence AN converges, that is to say the limit of this sequence is n, then that is the way that we will write down that the limit of the sequence an when n goes from 1 to infinity is equals to L. Or we can write down also that lim an and n tends to infinity equals to L. So, what is the definition of when a sequence has a limit? If we choose epsilon, that is a positive number, any positive number that could be as small as we would like, then we can actually find out a natural number NO, and for any n that is greater than NO, we get that an minus L is in the absolute value is less than epsilon. Okay, so the radius, so if the limit of the sequence is A, then the environment of A, the radius of the environment of A is epsilon. That is to say, if a sequence converges to A, then most of the members of the sequence must be located inside those two brackets, A minus epsilon, and A plus epsilon. So, in order that a sequence will be converged to A, then most of the members of the sequence must be located inside those two brackets. Then you can say that most of the members of the sequence are in the environment of A, because the radius of the environment of A is epsilon. Okay, so most of the members of the sequence that converge to A must be located inside those two brackets, A minus epsilon until A plus epsilon. That is to say, infinite members of the sequence that converge to A must be located inside those two brackets. And therefore, only a number that is not infinite of members can be outside those two brackets. Okay? Any number that is not infinite could be outside those two brackets. And because of the fact that inside any sequence that we are talking about contains infinite members or infinite elements, it means that infinite members of the sequence are located inside the vicinity of A. That is to say, inside members of the sequence are located inside those two brackets, and therefore the limit of the sequence will be equal to A. And because of the fact that epsilon could be as small as we would like, we can absolutely say that the limit of the sequence is A, because of the fact that epsilon could be as small as we would like. Okay, so you can choose epsilon, any epsilon that you would like. Epsilon actually it is a positive number, and then I will have, in order that the sequence will have a limit, I will have to find out a natural number NO, and for any n that is greater than NO, all the members of the sequence from NO that are greater than NO must be inside those two brackets. That is to say, infinite members of NO must be located between those two brackets. And because of the fact that infinite members of NO are located inside those two brackets, that is to say, infinite members of the sequence are located in the vicinity of A, and only fixed number of members are outside those two brackets. And because of the fact that only fixed number of members are outside of those two brackets, an infinite number of members are located inside the vicinity of A, we can absolutely say that A is the limit of the sequence. Okay? So, here, if the limit of the sequence AN is equals to L, then for any epsilon that you will choose, I can find out NO, and for any n that is greater than NO, then AN minus L will be less than epsilon. Okay, that is the definition of a limit of a sequence. Okay. So, intuitively, A is a limit of a sequence if the members of the sequence are getting closer and closer to A. Again, the members of the sequence are getting closer and closer to A as n increases, then A is the limit of the sequence. Okay? And this is a vague definition, but more accurate definition is that if for any epsilon that you will choose, if the limit of a sequence is A, then you can choose any radius of the environment of A, that is epsilon, and from NO, for any natural number n that is greater than NO, I can find NO in such a way that for any n that is greater than NO, then all the members that are greater than NO in their indexes will be located inside those two brackets. That is to say, infinite members of the sequence are located inside those two brackets, and only a fixed number, because of the fact that until NO we have n O indexes of the members of the sequence, it means that not infinite members of the sequence are located outside those two brackets, but infinite members of the sequence are located inside those two brackets. And for that reason, that is to say, infinite members of the sequence are located inside those two brackets. That is to say, infinite members of the sequence are located in the vicinity of A. And that is the reason that A is the limit of the sequence AN. Okay? And the radius of the environment of A is epsilon. So actually, each member that is inside those two brackets, the distance of each member that is inside those two brackets from A is less than epsilon. And therefore, because of the fact that infinite members of the sequence are located inside those two brackets, that is the vicinity of A is the limit of the sequence. Okay? Again, I repeat again that if L is the limit of sequence AN that contains infinite members, then for any epsilon that is positive, I can find out NO, and for any n that is greater than NO, we'll get that AN minus L is less than epsilon. That is to say, we can find out that infinite members that are inside those two brackets are located in the vicinity of the limit. And only fixed number of members are not located inside those two brackets. Okay? And you can also define limit in the broadest sense. You can say that sequence AN but before that, I will repeat on the definition of limit of a sequence that has a limit that is a finite. L is any real number. So if we have if the limit of sequence an when n goes from 1 to infinity equals to L, it means that for any epsilon that is greater than 0, there exists an O that is a natural number in such a way that for any n that is greater than an O, then an minus the limit that is L is the absolute value of an minus L is less than epsilon, or the limit L is equal to lim an when n tends to infinity equals to L. Okay, so for any epsilon that is greater than 0, we can find out NO that is a natural number in such a way that for any n that is greater than NO, then an minus L, the absolute value of an minus L is less than epsilon. Okay, that is the definition of finite limit. Okay, and a series sequence also can have a limit in the broadest sense. So the sequence an, the limit of the sequence an when n tends to infinity will be equal to plus infinity only if we can find out any large number m, and for any large number m we can find out NO that is a natural number, and for any n that is greater than NO we'll get that an is greater than m. In this way we actually proved that the members of the sequence are greater than any big number that you would like, because m could be any greater number that you would like. And in this way we proved that the members of the sequence, that is to say an, is greater than any big number, because m could be any big number that we would like, and still we can find out members of the sequence that are greater than m. Therefore the limit of the sequence an in the broadest sense will be equal to plus infinity, and in the same way we can actually define the limit of the sequence that is equal to minus infinity. Then we will choose a very negative number, and then we can find out, if we can find out NO in such a way that for any n that is greater than NO, we can find out that an is smaller than m. In this way we actually proved that this sequence is smaller than any number that we would like, and therefore the limit of the sequence will be equal to minus infinity. Okay, so it is very simple to talk about the limit of minus infinity. Therefore only write down only the definition of the limit of the plus infinity, and again, the limit of sequence an when n goes from 1 to plus n so is equal, the limit of sequence an when n equals to n goes from 1 to plus infinity will be equal to plus infinite if for any big number m we can find out no that belongs to the natural numbers, and for any n that is greater than no, then an will be greater than m itself. In this way we proved that the members of the sequence are greater than any number that we would like, and therefore the limit of the sequence will be equal to plus infinity. Okay? And we have the arithmetic of limits. If we have two sequences that converge, the sequence an converge to a finite limit, and the sequence bn also converge to a finite limit, then lim an plus bn when n tends to infinity will be equal to lim an plus lim bn. And the second rule is that if also we know that alpha is a constant number, so lim an times bn equals to lim an when n tends to infinity times lim bn when n tends to infinity. And rule number 3 states that lim alpha times bn equals to alpha times lim bn when n tends to infinity. That is to say, we can take out alpha out of the limit, and we can multiply alpha by the limit bn when n tends to infinity. And finally, rule number 4 states that lim an over bn when n tends to infinity will be equal to lim an when n tends to infinity over lim bn when n tends to infinity. And in this case, bn must not equals to 0 because it is not allowable to divide by 0. Here we have bn here, so because of the fact that it is not allowed to divide by 0, bn must not equal to 0, and also lim bn must not, when n tends to infinity, must not equals to 0. Okay? Thank you very much.